Hello. In this video, we're going to talk about the addition multiplication rule and introduce a little bit more about complements. First, we need to talk about how we can combine two events. First, the union of two events A and B is the event that either A occurs or B occurs or both occurs. We denote the union of two events with this U looking symbol. So we'd say A union B. We can describe its probability. The probability of A union B is the probability that in a single trial, either A occurs, B occurs, or they both occur. We can have an intersection of two events. The intersection of two events A and B, which we denote with kind of this upside down U, A intersects B, is the event that both A and B occur. And we can describe its probability. The probability of A intersect B is that probability that in a single trial, A and B occur at the same time, right? This one becomes a little bit difficult because there are going to be cases where A and B cannot happen at the same time, right? For example, think about rolling a dice where event A is rolling a 3 and event B is rolling an even number. You cannot at the same time roll a 3 and an even number, but we'll get to that example. From these definitions, we get an additional rule of probability, which we call the addition rule. And so given two events A and B, the probability of their union is the probability of A union B. That's going to be the probability of the event A, the probability of the event B, minus the probability of their intersection. Okay. The reason our addition rule is because within the probability of A and the probability of B, they both contain the probability that A intersect B occurs, right? That intersection is going to be contained in both. And so in a sense, if we just add these probabilities together, this value gets counted twice. Therefore, we get this almost discounting term because when we subtract kind of one, the probability of A intersect B, what happens is that 2 ends up canceling and we end up getting a good formula. So let's take a look at how this example will work, or how an example of this will work in the context of probability tables. Let's look at an example. Of 550 people, we want to know the probability that a randomly selected person either tests positive or uses drugs. Drug testing, pregnancy testing, efficacies of medications are very common examples because they do have these kind of two stages of you can have the quality or not have the quality and then test positive or negative for that same quality. So in this case, I want to know the probability that a randomly selected person either tests positive or uses these illicit substances. So we can let A be the event of testing positive and B be the event of using drugs. So by our addition rule, the probability of testing positive or using drugs is going to be the probability of A plus the probability of B minus the probability of their intersection. The probability of A is going to be the total number of people that test positive. Since I'm looking at this column, these are all of the people that test positive. That is going to be 70 out of 550. Next, I want to know the probability that someone uses drugs. Using drugs is this column, or this row, I'm sorry. Those are all of the people in this study that have used drugs before. That is going to be 50 over 555. Sorry, that's 555. Minus, now I want the intersection. I want only the people that test positive and use drugs. So here's the people that test positive. Here's the people that use drugs. I can find their intersection right here. That's going to be 45 out of 555. One thing you can notice is we have not reduced these fractions. right? Even though I can kind of reduce 70 over 555 or 50 out of 555, we're not going to because we're adding fractions here. And the way we have to add fractions, of course, is by getting a common denominator. If we already have one, we might as well just keep. If we do this, we're going to get 75 out of 555, or 15 out of 111. Right? That is how we use the addition rule. Sometimes two events cannot happen at the same time. We made reference to this earlier. Two events, we say, are mutually exclusive if when one event occurs, the other event cannot, and vice versa. Right? And we said a quick example would be rolling a 3 and then rolling an even number when trying to roll a dice. You cannot at the same time roll a 3 and an even number. Those are mutually exclusive. So how can we talk about the probability of their intersection? If I have mutually exclusive events, A and B, the probability that they occur at the same time is 0. Right? We made mention in the previous section that if an event cannot occur, we define the probability to be 0. Right? This definition of mutually exclusive events is saying that this event of A intersect B cannot occur. Therefore, we have no choice but to define its probability to be 0. One way we can really use this idea of mutually exclusive events is the idea we introduced at the end of the last video, which was complementary events, A and A complement. Right? If we have complementary events, we know that they cannot happen at the same time. Right? That is the definition of the complement. Recall, if I have an event A, the complement, which we have as A over bar, is all of the ways that the original event A cannot occur. But one thing we should notice that if I look at the probability that A or its complement occurs, if I look at the union, that thing has to be 1, right? Either A occurs or it doesn't occur. So the sum or that union has to be equal to 1. But we can use the addition rule to say that the probability of any union, specifically the probability of A union A complement, has to be the probability of A plus the probability of A complement minus the probability of their intersection. Well, A and A complement are mutually exclusive events, so their intersection, the probability of the intersection is 0, which means this term kind of goes away. And if I know this is equal to 1 and this goes away, what we end up getting is the probability of A plus the probability of its complement has to equal 1. Where this becomes very helpful is sometimes, and we'll see this especially in chapter 5 and in chapter 6, the probability of some event A may be difficult or nearly impossible to compute directly. So what we do is we not just think about an event in terms of the probability of A, but think about it as the probability of A complement. And if I look at this and solve this equation for the probability of A, I will get the probability of A is equal to 1 minus the probability of A complement. So let's look at just a quick example of how we can do this. So based on a journal article, the probability of a randomly selecting someone that has sleepwalked is 0.292. So the probability of sleepwalking is 0.292. If a person is randomly selected, find the probability of getting someone that has not sleptwalked. So we can say A is sleepwalking. That makes A complement not sleepwalking. And I know the probability of A plus the probability of A complement has to be 1. And if I'm looking for the probability of not sleepwalking, I get 1 minus the probability of A, 1 minus 0.292. That's going to be 0.708. Right? That is the probability of finding someone that has not sleptwalked. So earlier, we were able to compute the probability of the union and the intersection of two events because we had a probability table, sometimes we won't have all of that complete information, and we won't know the probability of the intersection of two events directly, and we'll have to compute it. And the way we compute this is another type of way that events can be related, and it's this idea of independence. So two events A and B are said to be independent provided the probability of an event A occurring does not change depending on whether or not B has occurred. So if event A can occur, whether or not B occurs, whether that probability doesn't change, we would say those two events are independent. On the other end, two events are dependent, provided that probability of one event does change, depending whether or not that other event has occurred. So for example, if I roll two dice, if I'm going to roll a 2 on the first roll of the dice and roll a 2 on the second roll of the dice, these are independent, right? Rolling dice does not affect the next roll, right? If I roll a 6 on one and roll a 4 on the other, that has no effect on whether that second dice roll is going to be a 4 or not. However, genetics is a really common example of dependent events. For example, male and colorblindness or male and baldness, they do affect it. If I'm looking at whether a person is male or whether a person is colorblind, that does have an effect, right? These are dependent, right? Males have higher rates of color blindness. So if I knew a person was male, that would change whether the probability of that person is colorblind. They are more likely to be colorblind. And so what we can do with this is talk about kind of restricting our sample space or restricting our population. So the probability that A occurs, given that B has already occurred, is called the conditional probability of A given B. And we denote it with this kind of little bar in between A and B. And the event after that little bar is our given, right? And this can, in fact, change the outcome of A, right? If we knew the person was colorblind, then I would know the probability that that person is male might be a little bit higher than kind of a 50-50 split of the genders, because males are more likely to be colorblind. And using this, we actually get a general multiplication rule for two events A and B. The probability that both A and B occur, so the probability of their intersection, is going to be the probability that A occurs times the probability that B occurs given A has occurred, or it's going to be the probability that B occurs times the probability that A occurs given B has already occurred. There are two different ways an experiment could happen, right? This first case is A is first. The second case is what happens if B is first, right? But in both cases, it is how we can compute the probability that both things occur. So let's do an example of this now. So in a color preference experiment, 8 toys are placed in a container, and the toys are identical except for the color. 2 are red and 6 are green. The child is asked to choose 2 toys to play with at random. What's the probability that they choose 2 red toys? So we can define the events R to be choosing a red toy and G to be choosing a green toy. And this really is going to help us come up with a tree diagram. So here, what happens if the boy chooses a red toy or the boy chooses a green toy? And then once we're here, the boy can either choose a red toy again or choose a green toy. Again, they can choose a red toy or choose Oops, sorry. Or choose a green toy. So with their first choice, right here, what is the probability that they choose a red toy? Well, at this point, it is 2/8. There are 2 red toys out of the 8. The probability that they've selected a green toy is 6 out of 8. In the next stage, once they've made a choice, what is the probability now that they've selected a red toy again? Well, now there is 1 red toy out of 7 total toys. What is the probability they've selected a green toy if they've selected a red toy first? There's still 6 green toys, but now there's 7 toys to choose from. We can fill this in as we move down, right? If they've selected a green toy first, there are still 2 red toys, but now there's only 7 toys to remain. What's the probability of selecting 2 green toys this way? Well, if they've selected 1 green toy, that reduced the total number of green toys left, and now we have 7, so that gives us that probability. So we want to know the probability that they chose 2 red toys, which is the probability they selected a red toy times the probability they select a red toy given they selected a red toy. So here, the probability of a red toy is 2/8. The probability of selecting a red toy given they have a red toy is 1/7, or 2/56, which reduces to 1/28. That's the probability in this example of choosing 2 red toys. Sometimes we may be asked to compute slightly different conditional probabilities. We can actually find the conditional probability if we already have the intersection. So the conditional probability of an event A, given that B has already occurred, the probability of A given B, is the probability of their intersection divided by the probability of B, given the probability of B is non-zero. Because of these 2 facts, the general multiplication rule and the conditional probability, we have a new way to test or to determine whether 2 events are independent. So 2 events A and B are independent, provided the probability of A given B is equal to A, and the probability of B given A is equal to B, right? What this is saying is that the conditional probability is unaffected by the fact that B has occurred. So that's what we would think, that if 2 events are independent, then the probability that A occurs given B occurs is not different than the probability that A happens. Likewise for B. One fact we get that is very helpful because of this is a multiplication rule for independent events. And this is helpful because we get to extend this rule to any number of independent events. So if A and B are events that are independent, then the probability of A intersect B is just the probability of A times the probability of B, right? That is only if those events are independent. Similarly, if I have 3 or more events, the probability of all of their intersections, so the probability of A intersect B intersect C, is just going to be the product of all of those probabilities. The probability of A times the probability of B times the probability of C. This is helpful for lots of different types of events. For example, coin flipping is independent. So if we want to know, for example, the probability of 2 tails, that's the same as the probability of tails and tails. That's just the probability of getting a tails times the probability of getting a tails. That's 1/2 times 1/2, which is a quarter, right? We can do kind of really nice things like that. The next idea that we want to talk a little bit more about is this idea of complements. We want to go a little bit further into the probability of complements. But this section is going to be split between the next 2 videos, so we will stop kind of right after we deal with complements. So again, we can extend this multiplication rule to include the probability that among several trials, you get at least one of some specified quantity or quality. the idea of getting at least one has the same meaning of one or more. So if A is the probability of getting at least, let's say, one success. The problem with this, and the thing that makes this kind of difficult, is if I want to compute the probability of A, this is going to be the probability of getting at least one success, but that means one or more. That means I want the probability of one success plus the probability of two successes plus the probability of three successes plus four successes plus dot, dot, dot. That's a lot of different simple events to keep in mind. And remember, when we defined events, we said if I want to look at an event, I can think of it as the union of all of its simple events. Well, if I want the probability of at least one success, that is the probability of exactly one success, exactly two successes, exactly three, exactly four, and so on. That might be really difficult or impossible to compute, right? There might actually be an infinite number of successes we could consider. What does the complement of A mean? Well, the complement of at least one success is getting exactly 0 successes, right? This means this in and of itself is a simple event, right? Getting 0 successes. That is very helpful. And so what this allows us to do is use this idea of complements we had in the previous video to find the probability of A, right? We can let A be the probability of getting at least one success. A complement is getting none of them. We can find the probability of a complement a lot of times by using this result up here, by multiplying these kind of independent events, and then compute the probability of A by using that complement formula of 1 minus the probability of the complement. So let's look at this example. A study by SquareTrade found that 6% of damaged iPads were damaged by the bag itself. Right? Not because of dropping, not because of user error, but something in the bag caused a scratch, caused a bend, or whatever. So if 20 damaged iPads are randomly selected, we want to find the probability of getting at least one that was damaged by the bag. So A is going to be the event of getting at least one damaged by the bag iPad. And then a complement is going to be the event of getting exactly 0 damaged iPads. And so we can compute the probability of getting exactly 0 damaged iPads, right? There are 20 iPads to pick from. Each of them is not damaged by the bag. So of those 20 iPads, the probability that the first one is not damaged by the bag is going to be the complement of that, right? 6% were damaged. That means 94% were not. So that means the first iPad not being damaged is 0.94 probability. The next iPad is 0.94 and 0.94. And all the way to the 20th iPad not being damaged is 0.94, which is 0.94 to the 20th, which if we compute that, we get 0.290. That's the probability that all 20 iPads were not damaged by the bag. That allows us to find the probability that at least one of these iPads were damaged by the bag by looking at the complement, or 1 minus 0.290 to get 0.710. That's the probability that at least one iPad is damaged by the bag or backpack itself. Okay, we will continue with the rest of this section in another video dealing with something called Bayes' theorem. This is slightly more difficult, and so we wanted to kind of devote an entire video to just trying to understand how Bayes' theorem is conducted. If you have any questions, let me know. If not, I will talk to you next time.